In this problem, we are now rotating about a different line, not one of the coordinate axes. So I'm going to try to draw this somewhat carefully so that we can see it. It's a little bit wide, right, because of the numbers, but we'll see what we can do. I have y equals x cubed, y equals 1. So on x cubed, when x equals 1, y equals 1. And let's see, we have 2 here. So let's call this 1, and let's call this 2, right? So this is x equals 1, x equals 2. Here's 2. But they also want the one y equals 1, so that would be here. This is the region they want. So that's what we're revolving. But then what are we revolving it around? We're revolving it around the line y equals -3. So 1, 2, 3 here. This is going to be the line that we're revolving it around. Y equals -3. All right, so this is going to be a little bit more difficult for me to draw. So just so that you can kind of imagine it down here, it's going to be a very wide guy, big hole, right? And we are still going to have those washers because we're going to have this thing with a hole in it. They're just going to be pretty wide because the hole is wide. So it's going to be kind of like this, you know? So there's the outer radius, and here's going to be my inner radius. And again, probably not the best picture, but then I'm also going to have the width of the washer itself. Now, the width of the washer itself is again going to be in the dx. Okay, so the idea with these, so that's the first thing, right? We are going around the line y equals -3. That's our axis. So parallel to the axis of rotation is our width of our washer, so that's in x. So basically the idea is the same as we had before. We're going to do the outer radius squared minus the inner radius squared times the height of our washer, which in this case is dx. Now, we know, and I kind of skipped this step, I just drew it in there. I have to be a little bit more careful. We know they gave us the x equals 2, and we know that this guy is x equals 1 because that is, of course, where the y equals x cubed and the y equals 1 curves, these two curves intersect at that point. So you have to think of this as what's the difference between these two curves? The top one is the curve y equals x cubed. The bottom one is the curve y equals 1. Okay. So, and the x equals 1 happens because x cubed equals 1 means that, of course, x equals 1, right? So it goes through 1, 1. Fine. So that gives us that. The question is now, what is the outer radius and what is the inner radius? Okay, because we have to get the axis of rotation into play because I can't just take, oh, the y, but I also have this extra piece. So what we want for the outer radius is the larger bit, and it's the distance. It's always going to be the distance from the axis of rotation. Okay, now notice the axis of rotation is at -3. Okay, so if I look at this arrow, this blue arrow that I just drew, the distance from the curve to the axis, this is going to be y. And the distance from this axis to the x-axis to the axis of rotation is going to be 3. right? That's absolute value of that distance, right? So when I look at what is going to be the whole length of that arrow, that's my R out, right? R out is y plus 3, okay? But the y that I'm talking about is the top curve, so this is going to be x cubed plus 3. So into my r out, I put x cubed plus 3, and that all is squared. Now my inner radius is kind of going to be the same thing, except instead of going up to the curve y equals x cubed, now I'm going up to the line y equals 1. So it's going to be 1 plus 3 or 4. I mean, you can see it's going to be 4. So, but I can kind of write it the same way just so that I'm consistent. Again, it's y plus 3. In fact, I can write it here, Rn also y plus 3, but now the y that we're going for is this line y equals 1, which is the inside radius. Okay. So this is what I end up with, and then all I have to do is do this integral. So I got x6, and I have 6x cubed, and I have 9. Oops. And I better make sure that this is a minus the way it's supposed to be a minus in what I originally wrote. Okay, so minus 16. That's much better. Otherwise, we'd really get the wrong answer. Okay. So this is not a hard integral to do. Once I have the setup, this is just a polynomial. Um, And I'll just go through the rest of that. X to the 7 over 7 plus 6x to the 4 over 4 minus 7x. And then we evaluate this antiderivative from 1 to 2. All right, we have to remember 2 to the 7th is 128. And what is this? This is 6/4 times 2 to the 4th is 16. And then this is 14. So these guys minus 1/7 plus 6/4 minus 7. Okay, so what I got here. Okay, so this is going to be 127. Um, This is gonna be, oh, what is this? This is gonna be 6 times 4, so this is going to be 24 minus 14 is 10, plus 7 is gonna be 17. So I got plus 17, minus this one is going to be a 3/2. Yeah. So now I'm going to make a common denominator of 14. Okay, so this is 7 times 2, 54. And this is going to be, this is a 5, 238, and then minus 21. So eventually I get a lovely wholesome answer of 471 over 14 pi, which is right. Okay. But going back, look at that. But going back, the crucial point here, besides the fact that I can't draw, is that when we're trying to figure out the inner and the outer radius, we're just going to look at the picture and we're going to figure out what that distance is. Think about it in terms of distances, right? The distance from, in this case, because you're in the negative, the distance from the axis, I don't know why it's doing that. I'm sorry, you guys. The distance from the axis x-axis to the axis of rotation is 3, so that just gets put into the total radius, right? Um, which we can write here as r. Okay?